Chromatography, very important conceptually. Basic concepts applied in lots of different ways. At its heart, when we talk about chromatography, we are talking about setting up a comparison between two, or taking a mixture of compounds, separating those compounds by polarity. We can either do that to basically just see what we have, like at a small scale, take a little bit on a little plate, or we can do it on what we call a preparative scale, which is to say, put a bucket in, get smaller buckets out of pure stuff, okay? And so either that, we can either get it out at the end, or we can just do it on a small scale and don't worry about getting it back out at the end. At the root of every chromatography is that it's a competition for compound between two phases, a mobile phase and a stationary phase. And stationary is exactly what it sounds like. Stationary phase stays put, mobile phase flows over it, and compounds have a choice. Do they want to stick on the stationary phase, or do they want to go with the mobile phase that's going over it? All right, that's our main point here. That is true for all chromatography. There's always a stationary phase, always a mobile phase. The one that you are going to be running in lab next week or later, the one that I use a ton in my synthetic group is called TLC, thin layer chromatography. All right, again, these are descriptive words. It's a thin layer. It is a plate, sometimes glass backed, sometimes like aluminum backed, once in a while plastic, not often. But on that surface, there's a very, very thin layer of silica gel. So silica gel, you might remember, and when you buy shoes, there's a little packet and it says do not eat, but you eat it, and it's okay, but it's not great. So this is silica gel like that, but it's not big balls of it. It's really, really fine powder, really fine, a little bit too fine. It's actually an inhalation hazard. But that silica gel is very, very polar. All right, so yes, it's mostly silicon and oxygen, but the surface of it has lots of these OH groups called a silanol. Silanol is SiOH, okay? Those silanol groups are very, very polar. So what that means is that polar compounds want to stick to the silica gel. It also kind of means that nonpolar compounds kind of want to stick to it too, right? Because you can think of a nonpolar compound, if I put a pretty big dipole here, right, a big bar magnet, that's going to induce London forces there. So it's not like nonpolar things won't stick at all. Some nonpolar things will stick at least a little bit. Okay, but that's our stationary phase. Our stationary phase is silica gel, and it is polar. So compounds will stick. My nonpolar, my mobile phase is going to be solvent, and that's going to be nonpolar. So I'm going to put a very shallow little pool of solvent here. It's called an eluent, or the mobile phase, and that is nonpolar. All right, so it's not water. It's like hexanes, or maybe some, ketone or ester that's a little bit more polar than hexanes, okay? Chromatography is essentially a competition, all right? If I use hexanes, then hexane is a poor competitor with silica gel for compounds, all right? So I would say that hexanes I would call a weak eluent. So maybe if you've got a compound that is very, very nonpolar, not sticky at all, maybe it would choose hexanes and run with the hexanes and not stick to the plate. But most things are at least a little bit sticky. And so something like hexanes would have a hard time convincing it to come off the plate and go, okay? And so operationally, what does that look like? Operationally, that would mean, all right, I've got my little shallow pool of solvent, and I've got my spot on an X right here. I'm going to put my mixture of compounds on that spot. All right, so there's a bunch of stuff piled up there. When I drop it in the little jar, the solvent is going to creep up the plate. So if you've done paper chromatography, you're familiar with this, right? If I put paper and water. I see the paper, I see the water flow up the paper. This is the same concept, right? So non-polar things are more likely to go into the non-polar eluent and travel, maybe ending up here, right? So my solvent, let's say it gets this high. I've got some spots that end up here. Maybe I've got other spots that don't travel as far because they like the silica a little better, okay? I don't need to use hexane, so I could use a more polar solvent, let's say like acetone. Acetone is a ketone, nail polish remover, right? So acetone is more polar, and so it's going to compete better for the spot with silica gel. So acetone is a more powerful eluent, which is to say, polar solvents, spot travels more. The more polar the solvent, the further my spot's going to travel. So if I just have hexanes, for instance, and I run this, maybe nothing in my mixture decides to go with the hexanes up. If I go with a 1-to-1 mixture, maybe my spots decide to look like this. And then if I just use straight acetone, now it pushes it more up the plate, and maybe they're like all the way up here now. Okay, so the more polar solvent is going to push it further up the plate, and that is true for no matter what the compound is. Which is to say, my order of spots isn't going to flip if I change solvent, for the most part. Okay, we can put a number to how far the spot goes up the plate. It's just a fraction. We would say the solvent traveled, let's say, this far. The solvent traveled this far in total, and maybe this spot traveled this far. We can take that fraction. We can take that fraction here, and that is called the retention factor. So let's say this is 2 centimeters and this is 3 centimeters. My retention factor would be 2/3. Retention factor, RF, would be 2/3, or 0.67. So again, we can measure kind of the fraction our spot goes up the plate in a specific solvent. So the retention factor should depend on the compound I'm looking at and the solvent that I'm using. And so if I run this reaction a lot, and I use the same solvent for the TLC, I should see it travel the same time and the same amount every time. Usually when I do TLC, I'm comparing more than one thing. So let me share a screen here. Nope. Okay. This is what a TLC might look like. So here we're looking at 6 different mixtures, I think, of a drug, headache medicine at once. Okay, and we can do this. We can look at lots of things at once. One of the questions that TLC is trying to answer is, are things the same or are they different? Okay, so when I look at this TLC, what I'm seeing is I've got a bunch of compounds. These compounds look like they might be the same. Do I know that they're absolutely definitely the same? No, there could be lots of compounds that just happen to go that far up the plate. All right, but they're not obviously different. Okay, so if I'm comparing, 1 and 2 here, I would say that, okay, maybe this thing that looks like it's pure in line 2, that's also present in number 1. Okay, and I also say that the higher the spot goes at the plate, the less polar it is. Right? And so again, this is how we use it. We use TLC to answer a question. Here, my question is, okay, which is the same and which are different. It looks like those spots might be the same. It looks like these spots might be the same. Looks like these spots might be the same. And this is different because it's a different RF. Okay, so that's what a TLC looks like. All right, so we can also do this to actually get a pure compound out of a mixture. If I want to separate a mixture like maybe a half a gram or a gram worth of some oily mixture, then I will essentially run this in a tube. So I'll have a column of silica gel, still polar. I will put my stuff on top of that. So I'll take my mixture and kind of add it to the top of this column. And then I will put solvent or eluent kind of from the top and collect it in the bottom in test tubes or flasks like that. So this is just like TLC. The non-polar stuff will go fast because it doesn't stick. The polar stuff will run slow because it is sticking. All right, the biggest difference between TLC is that A, this is upside down because solvent is flowing top to bottom, not bottom to top. And B, I'm actually collecting stuff at the bottom as it comes off the column. Here's a really, really nice column. It usually doesn't look like this, mostly because the stuff we make is usually not colored. But here, somebody is clearly starting with a mixture of a bunch of different colored compounds. All right, so it's kind of you start at the left, and it's kind of like progressing left to right, like through time. Okay. So what you can see is that yellow band at the bottom has traveled the furthest. That tells me that that yellow band is the least polar because non-polar stuff runs on silica. And the darker colors are more polar because they are sticking more. So as I go left to right, I'm adding solvent on the top and I'm draining solvent in the bottom in like different flasks or different test tubes. And you can see, again, the yellow band is running much faster than the other bands. And in the last picture there, you can see then you're starting to actually collect the yellow stuff individually on its own. And you've purified it. That's what purification is. So again, very similar to TLC, just three-dimensional and upside down. But the concept is that non-polar compounds stick, or non-polar compounds run, polar compounds stick. Okay, questions so far? Okay, so those are the two biggest things that you're going to have like hands-on practice with a lot in my lab or in the lab here. So some other things where you might encounter this is one is HPLC, so high performance. So HPLC is also with columns. I also have, my stationary phase is the column, my mobile phase is going through it. Different compounds take different amount of time to come through. The biggest difference here is that HPLC is reverse phase. For like engineering, practical, other reasons, our column works better, in this case, when it is non-polar. So they actually take a silica column and they just kind of like staple a bunch of like long, greasy carbon chains all around it. All right, so there's like C8, C16, very, very long carbon chains that make our column really, really greasy and non-polar and frankly gross. Now, this is now everything we knew about column chromatography, we now flip on its head. So before, our weak eluent was the most non-polar thing we could think of, hexanes. Now, our weakest solvent is the most polar thing we can think of, which is to say water. Okay. Not before, I said non-polar stuff ran down that column, polar stuff sticks. Now, polar stuff will run and non-polar stuff will stick, which is great because now I can look at really, really polar biological molecules, proteins, amino acids, all that kind of stuff, sugars, it's great. And so again, HPLC, whenever you see LC in the literature, like LCMS or LC whatever, they're usually talking about reverse phase stuff where the column is non-polar and the mobile phase is polar. The other C you'll see a lot is GC, gas chromatography. This is just like it sounds. Instead of solvent being the eluent, now we have a gas, helium, probably. Helium, maybe even air, is like carrying a solvent through a column. The column is usually coated with some sticky stuff that the compound can either stick to or not. So that's the biggest difference is there's no solvent, it's just gas. The other difference is the size of the column. For our columns or for HPLC columns, your column is maybe 6 inches, maybe 12 inches tops. Your GC column is 30 meters. And the way that works is that the column, these columns are that thick to that thick, whereas this column is like as thick as a human hair. It looks like a wire. And so a 30 meter GC column takes up about that much space because it's like it looks like a little gold wire that's kind of like looped a mess of times. Okay, but again, you inject some compound. It's usually run pretty hot, so it's in the gas phase. The gas, carries it through the column. It separates by polarity, and then it comes out the other end. Okay. So that's chromatography in a nutshell. You are separating a mixture of compounds by polarity. They used to say polarity. A lot of times you'll have a stationary phase and a mobile phase. Your mobile phase is usually a solvent. When we do TLC and column chromatography, we have a non-polar solvent and a polar stationary phase made from silica gel. And so non-polar stuff runs, polar stuff sticks. HPLC is backwards, and GC is forwards. You're still non-polar stuff is going to run faster, but it's in the gas phase, not the liquid phase.